Welcome to Chemistry with Caroline. In this video, we're going to look at the hydration of alkenes. So this is a reversible reaction that is acid catalyzed. You can take an alkene starting material. So here would be your alkene here. You can add water in the presence of an acid catalyst, and then you can get, as a product, an alcohol. You could also take an alcohol, and under acid catalyzed conditions, you could make an alkene. So we can control this reaction by modifying the amount of water present. So water is a reactant. If we add H2O, you're going to shift towards the alcohol, right? If we have excess water, we can push the equilibrium towards the alcohol, so it's like a dilute acid that is catalyzing. If we remove water, then we're going to push the equilibrium towards the alkene, so we can make the double bond. So in this video, we're going to look at the formation of the alcohol. You can see that a double bond is going to span two carbons, right? So there's essentially two spots where the alcohol could add, but it will only add to the more substituted carbon if you start with an asymmetrical double bond. This type of addition, where OH or X adds to the more substituted carbon, is called a Markovnikov addition. So let's go to the next slide and we'll take a look at the mechanism. So the reason this reaction is reversible is because alkenes are susceptible to acid. If you think about a pi bond, it's just electrons that are above and below the plane of the molecule. They're more available and accessible. They're negatively charged, of course, as electrons, so they're going to be attracted to a positively charged proton. And so that proton is going to add to one of those carbons, and one of them is going to end up with a charge. So if I think about my starting material, I have a secondary carbon on the left-hand side and a tertiary carbon on the right-hand side. We know that carbocations are more stable the more substituted they are. So the H is going to go to the less substituted carbon so that the carbocation generated is on the more substituted carbon. So in this case, the tertiary carbocation, which is much more stable. So now that I have a carbocation electrophile, my nucleophile, which is water, can come in and attack. So this looks a little bit like an SN1 type reaction here. I'm using equilibrium arrows because this is reversible the entire way because of these acidic conditions. So I make this intermediate where I have essentially the alcohol, but it needs to be deprotonated. And so we have, remember, an excess of water in this reaction because we're trying to push the equilibrium towards the alcohol product. And so a lone pair on another water can come in acting as a base, and it can deprotonate that species to give me the neutral organic product. So there is my final product, the alcohol. So it's just a couple step reaction. You have protonation of the pi bond by the proton, the acidic protons in solution. That will generate only the most stable carbocation. So if your alkene is asymmetrical to begin with, you will end with a carbocation on the more substituted carbon. This is called a Markovnikov type addition when the electrophile generated is on the more substituted carbon, and so the X group adds to it. The water comes in and attacks, forming a new bond, and then that alcohol will be deprotonated by another water molecule in solution to give the final product. So this has been a look at the hydration of alkenes. If you found this video helpful, please like, subscribe, and share with your friends.